Let me welcome you to this lecture. We have already learned how we can use the x, y, z the functions or the linear functions x, y, and z as basis, or how these functions transform as in different point groups. We have also written matrix representation by taking x, y, z as the basis, and also what we have seen is that the p orbitals as well as the translational modes of symmetry in a molecule essentially are uh, exactly same, the way transform as exactly same way the way x, y, and z transforms as, and that is why finding out the how these functions x, y, and z transforms as is interesting from chemistry point of view, because we also learn how the p orbitals transform as well as how these translational modes of symmetry transforms as. Now, during this lecture, we will learn how quadratic functions, or how we can find out the reducible representation by taking quadratic functions as basis. And the quadratic functions which are of interest to us are the functions which describe the d orbitals essentially. So we will take these functions as the basis and then find out how these functions transform as in a particular point group. So the point group that we will take is the octahedral OH point group here to illustrate how we can do this exercise. So let us take the octahedral point group and let us try to write a reducible representation by taking the quadratic functions which describe the d orbitals as the basis. So let us first write the symmetry operations in octahedral point group so that we can write the reducible representation afterwards. So the octahedral point group, there are 48 symmetry operations we have already learned. That is, one is identity, then we have 8 C3 axis, 8 C3 symmetry operations. These are coming from 4 different C3 operations which passes through the opposite triangular faces in an octahedron. Then we have 6 C2 axis of symmetry, which again are not collinear with the principal axis, that is the C4 axis of symmetry, and these bisects the sigma h planes, essentially these C2 axes. Then we have the 6 C4 operations coming from 3 C4 axis of symmetry, and collinear to these C4 there are 3 C2 axes as well, which essentially are coming from the C4-2 symmetry operations. Then these are the only proper axis of symmetries or symmetry operations based on proper axis of symmetry. Then we have the inversion operation. We also have 6 S4 axis of symmetry, 6 S4 symmetry operations. Then coming from 3 S4 axis of symmetry, then we have 8 S6 operations, as well as we have 3 sigma H plane of symmetry, and then we have 6 sigma D planes of symmetry. So these are the 48 symmetry operations in octahedral point group, and now we will find out how the d orbitals will essentially transform as under these octahedral symmetry. So before we do that, first let us find out how the symmetry operations, or how the because there are 5 d orbitals, so let's call these d orbitals, or let's write the functions for these d orbitals instead of looking at the lobes of the d orbitals and how these lobes changes upon performing a particular symmetry operations, because here in this case we have several uh, uh, symmetry operations, and it may be difficult for us to visualize how the lobes transforms as when we perform a certain symmetry operation and then deduce the character. So instead of that, we will take a different approach, a more mathematical approach, where we will see how the functions describing these d orbitals will transform as under a given symmetry operations. So let's first write the functions, quadratic functions which describe the d orbitals, and let's label them as this xy function, let's label it as phi1, and x2, xz function as phi2, then we have also yz function as function phi3, then we have x square minus y square, let's label it as phi4 function, and then we have also the function for dz square orbital. Now when we write dz square orbital, the function for this dz square orbital is 2z square minus x square minus y square. So in order to get it correctly, how the d orbitals transform as, we need to write the function, complete function for dz square orbital, not only take it as only z square. So these are the functions describing different d orbitals. Now we know that we have 5 different functions. So this matrix representation for different symmetry operations, if we take the d orbitals as the basis, it will be a 5-dimensional matrix, and the matrix, the character of the matrix for the identity operation is going to be equal to 5. So that is for, if you take the d orbitals as the basis, because all the d orbitals, they will not change direction as well as orientation when we do identity operation. So the character, we will have a 5-dimensional unit matrix for the identity operation, and the character is going to be equal to 5. Now let us find out what is going to be the character, or what is going to be the matrix representation for the C3 operations, which we take the d orbitals as the basis. Now this is quite complicated, or this looks quite a daunting task, because we know that if we draw an octahedral here, say, so the C3 axis passes through the center of 2 triangular faces in this way, and let's assume this to be the z-axis, this to be the x, and this to be the y-axis, y-coordinate here. So if this is the origin, from here it will go in this way. So now it is quite difficult for us to imagine how the xy or dxy orbital will move when we do the C3 symmetry operation, when we do a C3 operation with respect to this particular C3 axis. So that is why we first need to find out how x, y, and z transforms as, before we find out how these d orbital are going to transform as under these when we perform the C3 symmetry operation. So when we do C3 operation, what we see here is that the x-axis or x coordinate will move towards the y, or will move to y, and y will go to the position of z, while z will come to the position of x. This is, one can more easily visualize how x will behave when we do C3 operation. If you look at the triangular picture for an octahedron, we have already done it. So the C3 axis now passes through the center of this these triangles, opposite triangles over here, and if we level this position as 1, 2, and 3, so then let's call it, say, 1, 2, and 3, then we know this is through this, so z-axis is going through this x-axis is going through, and through this y-axis is going through. So when we do C3 operation, x will go to the position of y, y will go to the position of z, and z will come to the position of x. So that is how we can get this. So we know how the x, y, and z coordinates transform, and or how the functions x, y, and z transform as when we do C3 operation. So let us find out now what is going to happen if we do C3 on phi1. So when we do C3 on phi1, that is when we do C3 on xz, so we know upon performing C3 on x, it goes to y, and upon performing C3 on Z, it goes to X. So it becomes XY essentially, and so this is equal to, sorry, this is XY, phi 1 is XY, so X transforms as Y, Y transforms as Z. So this is YZ, YZ is nothing but our phi 3. So when we do C3 on phi 1, it becomes phi 3. Similarly, when we do C3 on phi 2, but we see that it is XZ, so X transform as Y and Z transforms as X. So this is XY, which is your phi 1, and then when we do C3 on phi 3, what we get is C3 YZ will transform as Y transforms as Z, and Z transforms as X. So this is XZ, which is nothing but your phi 2. Then we have the other two functions, phi 4 and phi 5. So let us also do those two. So when we do C3 on phi 4, what we have is C3 on x squared minus y squared. So x transform as y, so this will become x squared will become y squared, and y squared will become z squared. So now we need to express this result in terms of the functions phi 1, phi 2, phi 3, phi 4 or phi 5, and if you look carefully here, a little bit of mathematics will tell us that this is going to be equal to minus half phi 4. So that will give us plus y squared here minus x squared. Then minus half phi 5. So this, if we do, we will get essentially, so let's also write these to get, so then we have more space. Phi 2. So if you expand this, let us expand this just to prove that this is equal to minus y square minus z square. So if we do minus half phi 4, that is x square minus y square minus half 2z square, that is phi 5 minus x square minus y square. So if we do so, so this is minus x square by 2 plus y square by 2 minus z square is going to be left here plus x square by 2 plus y square by 2. So this minus x square by 2 plus x square by 2 will get cancelled out here. Y square by 2 will give us total y square and minus z square. So what we see is that this essentially minus y square minus z square, this result that we obtain when we do C3 operation on phi 4, we could express this in terms of phi 1, phi 4 and phi 5. So that is phi 4 transforms as minus half phi 4 minus half phi 5. So then let's also do C3 on phi 5. So what we have here is that 2z squared, so that transforms as x, so we will have 2x squared here. Then we have a minus x squared, x transforms as y, so this will be minus y squared. And then we have minus y squared, y transforms as z, So that is minus z square. So this is the result that we will obtain when we do C3 operation on phi function. So we will have to again express this function in terms of I know any one of these functions or some of some algebraic relation between these functions. So that we will obtain if we do so 2x square. So let's write 3 by 2 5 4 minus half 5 5. If we do so, what we will get 3 by 2 x square minus y square minus half 2 z square minus x square minus y square. Let us elaborate here. So 3 by 2, 3x square minus by 2 minus 3y square by 2 minus, that is z square, plus x square by 2 plus y square by 2. So that is going to be equal to, because this is 3x square by 2 plus x square by 2, it will be 4x square by 2, which is equal to 2x square, minus 3y square plus y square by 2, minus 3y square by 2 plus y square by 2 will give us essentially 2y square by 2, which will be equal to minus y square, and then we have z square. So what we see here, the function that we get over here after doing a C3 operation on phi is essentially it is equal to 3 by 2 5 4 minus half phi, because that is what we get essentially when we do this. Expand this expression. So we know that phi transforms as 3 by 2 phi 4 minus half phi. So now we know how these functions transform as how the different functions for different d orbitals transforms as when we do the C3 symmetry operation. So we can write the matrix representation for the C3 symmetry operation. That is, we know phi 1, phi 2, phi 3, phi 4, phi 5. Let's take all the functions of the d orbitals as the basis. Let us do C3 symmetry operation. Then what we will have, we know phi 1 transforms as phi 3. So here we will have phi 3. Phi 2 transforms as phi 1 here. Phi 3 transforms as phi 2. And phi 4 transforms as minus half phi 4 minus half phi 5. Then phi 5 transforms as 3 by 2 phi 4 minus half phi 5. So this is the resulting matrix that we will obtain when we do C3 operation on these, if we take these functions as the basis, the functions for the d orbitals as the basis. So now we can write the matrix representation for the C3 operation, because the result when we do C3 on these functions, we get this as the result. So the symmetry matrix representation for C3 operation must be 0 0 1 0 0 1 0 0 0 0 0 1 0 0 0 and 0 0 0, that is minus half, because we have minus half phi 4, then only if you put minus half here, then only we'll get this, and then minus half here also. So then for this one 0 0 0 3 by 2 and then minus half. So this is the matrix representation for the C3 symmetry operation for when we take the d orbitals as the basis. So let's keep these and let's rewrite a matrix representation for C3 operation here. So we will proceed further and we will try to figure out again now the character for the C3 operation, if we find out from here, is going to be equal to -1. So for the reducible representation, well, by taking the d orbitals as the basis, we could find out that the character for the C3 operation or this symmetry operations in the C3 class essentially is going to be equal to -1. And we have written matrix representation for one of the C3 operation, that is C3-1 operation for the C3 axis that we have already drawn for in an octahedral. For that particular C3-1 operation, this is the matrix representation. You can similarly write matrix representation for other C3 operations in this class also. But as we know that the character of all the matrices for symmetry operations within the same class are going to be same, so that is why we can write -1 here, because we know that the character for all the matrix representation for all the C3 operations are going to be -1 here. So then let us proceed further and let's also write, try to figure out what is going to be the matrix representation for the C2 operation, or what is going to be the character for the C2 operation. Now when we do C2 operation here, let us redraw the octahedron. So these C2 axis of symmetry passes through or bisects the sigma h planes essentially. So we can assume, now let us take this C2 axis of symmetry which bisects this sigma h plane over here. This is the C2 axis. So if this is the x, this is the y that we have taken, and this is the z. So when we do this C2 axis operation, x will go to y, we can see that, and y will go to x, and z will go to -z, as we can see. So xy will become xy because x will become y, y becomes x, so xy remains xy itself. So phi1 will go to phi1, and phi2, which is xz, because x becomes y, z becomes -z, so phi2 is going to be equal to -yz. Then that is equal to essentially minus of phi3. So then if we do phi3 is yz, y becomes x, z becomes -z, so this is going to be minus xz, which is nothing but minus of phi2. So then let us also do x square minus y square. So this is phi4. So x square essentially becomes y square, and y square will become x square. So the function is going to become y square minus x square, which is nothing but actually minus of phi4. Then we have phi5. So 2z square, z becomes minus z, but 2z square is there, so that is why it will remain as 2z square only. Minus x square, that will become minus y square. Minus y square will become minus x square. So essentially, phi5 remains phi5. It does not change. So the matrix representation for the C2 operation again we can write based on this, because phi1 remains phi1, 1, 0, 0, 0, 0. Then phi2 becomes minus phi3, 0, 0, minus 1, 0, 0. Phi3 3 becomes minus phi 2, and phi 4 is minus phi 4, 0, 0, 0, minus 1, 0, and phi 5 is phi 5 itself. So this is a matrix representation for the C2 symmetry operation, and then if we look at the character here, this is going to be equal to plus 1. So now let us also go to find out the symmetry matrix, the character for the C4 symmetry operation when we do the when we take the d orbitals as the basis. Now we can use the same strategy here, the one that we have used for C3 as well as for the C2 operation. But since these C4 axis passes through the Z axis here, or collinear with the Z axis, so we have a generic equation or generic equation to find out the character of the C4 operation here, or for the generic equation to find out the character for a symmetry operation, that is Cn1 is equal to 4 cos square 360 by n theta, that is plus 2 cos 360 by n minus 1. So if we put here, because this is 4, so we have C4 axis of symmetry, so this is theta is equal to 90 here, and then cos 90 we know is equal to 0, so that is why 4 cos square theta, this is going to be 0, this will also be equal to 0, and we will be only left with minus 1, and the character for the C4 operation is equal to minus 1, that we can write straightforward. Now for the DC2, we know these are again collinear to the Z axis, and we only need to change the theta here. Theta is going to be equal to 180. So cos 180 we know is equal to minus 1. So this is when we put cos 180. So minus 1, so minus 1, so cos minus 1 into minus 1, because we have cos square theta here. And then we have 2 cos 180, which is minus 1, and then minus 1 here. So this is going to be equal to plus 4 minus 2 minus 1, which is going to be equal to plus 1. So now for the inversion operation also we can do, because we know when we do inversion, x goes to minus x, y goes to minus y, z goes to minus z. So then these functions phi 1 xy will become minus x into minus y, which is going to be equal to plus xy only, and which is phi 1 only. Xz is going to become xz only again, because minus x into minus z will give us plus xz, and that is equal to phi 2 only. Similarly, phi 3 is also going to be phi 3, and phi 4 again we see this is also quadratic function. X square when we do minus x square will give us plus x square. Similarly, minus y square will give us plus y square. So essentially this will remain same. So that is also phi 4 also remains phi 4, and phi 5 will also remain phi 5 when we do this. So what we have here is, again, we'll have the character of the matrix is going to be equal to plus 5 here as well. So then we have S4 symmetry operation. Again, these S4 symmetry operations are collinear with the or the S4 axis of symmetry are collinear with the Z axis over here, or collinear with the C4 as well as the C2 axis of symmetry, and that is why again we have a generic equation to find out the character of these matrix representation for such symmetry operations, which are collinear with the principal axis or collinear with the Z axis over here. And of course we can also use this strategy to find out the matrix itself and as well as the character of the matrix. But the generic equation for Sn1 operation, or character of Sn1 operation, matrix representing Sn1 operation, is 4 cos square theta minus 2 cos theta minus 1. So instead of plus 2 cos theta in case of CN operation, we have now minus 2 cos theta and minus 1 over here. So for S4 operation, we know cos theta is going to be equal to 0 because theta is equal to 90. So the character is going to be equal to minus 1 here as well. So then we have the S6 axis of symmetry, which are again collinear with the C3 axis of symmetry, and we cannot use the generic formula here to find out the character of the S6 operation or matrix representing S6 operation, and we will have to proceed the way we have done it for the earlier times. So again, now we should see how X, Y, and Z are going to transform as when we do this S6 operation, and for that again it is better to write, or in order to visualize how X, Y, and Z are going to transform as, it is better to look at it, draw this triangular picture of octahedron, and let's level this again 1, 2, and 3. 1 is along Z, and this is 2 is X, along 3 we have Y axis, and this is the position that is minus Y, this is minus X, and this is minus Z. So now when we do C6 operation, and then we do sigma perpendicular to C6, that is the C6 axis is perpendicular to the plane of the board, the way we have drawn this triangle over here. So the plane is going to be, the plane where we do reflection is essentially the plane on the on the plane of this board. And then when we do C6 first, so X will go to this position over here above minus Z, but when we do sigma H on sigma H, X will go to the place of minus Z. So X is essentially minus Z. So similarly, Y will go to the above minus X when we do C6, and when we do the sigma perpendicular to the C6, it will go to minus X here, and Z will go to minus Y. That is what we see. So from here, we can find out how these phi 1, phi 2, and phi 3 are going to transform as. So phi 1, that is xy, x transforms as minus z, y transforms as minus x. So this is xz, which is nothing but phi 2. So phi 2 transforms, that is xz, x is minus z, z is minus y, so this is going to be yz, so which is phi 3, and phi 3, that is yz, y is minus x, z is minus y, so this is xy, and that is going to be phi 1, phi 1. Now phi 4 is going to be a little bit complicated, so let us do S6 on phi 4, that is S6 on x square minus y square over here. So we know x becomes minus z, so this is going to be plus z square when we do S6 operation on x square function over here, and y square will essentially give us x square. So the sign is not going to change because when we do square, the minus sign over here will go, and this is what we end up with when we do S6 on phi 4 operation. And again, the way we did it for the C3 operation, we have seen, we will have to do it for this function also. We will have to express in terms of these, this phi 1, phi 2, phi 3, or phi 4, or phi 5. So that is what we will have to do here. So plus z square minus x square, that we will get if we do minus half phi 4 plus half phi 5. Let's see if it is correct or wrong, because if we do minus half phi 4, that will give us minus x square by 2 plus y square by 2. Then let us write this part. So this is is going to be z square minus x square by 2 minus y square by 2. So that is going to be plus y square by 2 minus y square by 2 will cancel each other here, and we have plus z square and minus x square by 2 minus x square by 2. So essentially minus 2x square by 2, which is going to be equal to minus x square. So that is what we obtained because this is same. So that means we have written the expression in terms of phi 4 and phi 5 now here. So phi 4 transforms as minus half phi 4 plus half phi 5. So let us also see how phi 5 is going to transform as. So S6 phi 5, which is S6 2z square minus x square minus y square here. So z square, z transforms as y. So this is 2y square minus x transforms as z. So z square minus y is x square. So this is what it is. So this, if we want to write in terms of phi 4 and phi 5, we will have minus 3 by 2 phi 4 minus half phi 5. Let's see if it is correct or wrong. Minus 3 by 2 x square plus 3 by 2 y square minus z square plus x square by 2 plus y square by 2 if we put phi 4 and phi 5 over here, and that will give, because this is minus 3x square by 2 plus x square by 2, so that is going to be equal to minus 2x square by 2, which is minus x square, plus 3y square by 2 plus y square by 2. So this is going to be equal to plus 2y square and minus z square. So which is essentially the function that we obtained when we do S5 operation on phi 5. So that is why this is equal to phi 5 transforms as minus 3 by 2 phi 4 minus half phi 5. So we can now write the matrix representation for S6 operation as well, because phi 1 transforms as phi 2. So this is what will be. Phi 2 transforms as phi 3. Phi 3 transforms as phi 1. And phi 4 transforms as minus half phi 4 and plus half phi 5. And minus 3 by 2 phi 4 here, minus 3 by 2 and minus half. So this is what is the matrix representation for S6 operation, and if we have to write the character, we can write that the character is equal to minus 1. So similarly, we can also find out for sigma h here, because when we do sigma h, x will remain x, y will remain y, z will remain go to minus z. If we consider this equatorial plane over here, then this is what is the situation, and then phi 1 will remain, this is xy, so this becomes xy. Phi 2 is xz, so it is minus xz, so this is phi 1 itself. So phi 2 is going to become minus xz, so then it becomes minus phi 2, and phi 3 is going to become minus yz, so that is minus phi 3. Phi 4, which is x square minus y square, remains phi 4 itself, and phi 5 also remains phi 5, does not change. So the matrix for sigma h as well we can write is going to be 1 0 0 0 0 0 minus 1 0 0 0 0 minus 1 0 0 0 0 0 1 0 0 0 0 0 1. So this is what is the matrix for sigma h, and the character of this matrix is equal to +1. So similarly, we can also do it for sigma d here. We know sigma d, if you take ML6 complex, octahedral ML6 complex, the sigma d is going to contain 2 of the ligands and the metal center. So then in that case, X will, that is, it contains the C2 axis essentially. For this sigma d, we will find out X will go to Y will go to X, and Z will remain Z. So function xy remains xy, so phi1 remains phi1. Function xz will become yz, so that is yz is phi3, and function yz will become xz, and that is phi2, and phi4 it is x square minus y square. It will become y square minus x square, and that is why it is minus phi 4. And this one will become phi 5, will remain as phi 5 itself, and that is why the matrix for sigma t is 1 0 0 0 0 0 0 1 0 0 0 1 0 0 0 and 0 0 0 minus 1 0 0 0 0 0 1. So this is what is the matrix for these sigma, one of these sigma d operation over here, and the character of this matrix is again equal to +1. So this is how we can find out the character of different symmetry operations by taking the d orbitals as the basis. Now we already know, we have learned in undergraduate itself, that in case of the octahedral point group, or in octahedral geometry, the d orbitals essentially transforms as T2G or an easy symmetry. We know that the xz, yz and the xy orbitals, they essentially transform as T2G symmetry, and then the x square minus y square and dz square orbital, this transforms as easy irreducible representation. Now that means we will have, if we take this reducible representation that we obtain by taking the d orbitals as the basis and find out the irreducible components of this reducible representation, we will obtain two irreducible representations, that is T2G and EZ. So this 5-dimensional reducible representation can be block factorized into two irreducible representation. One is 2-dimensional representation and the other one is a 3-dimensional representation. And if you look carefully in these matrix representation, we will see that it is easy to figure out. Also, we know that the x square minus y square and the z square orbital, which is phi 4 and phi 5 functions, essentially they transform together, while the phi 1, phi 2 and phi 3, they transforms together as irreducible representations. So we can block factorize these matrices here in this way. And if you look at the character of these block factorized matrices now, you can verify with the character table for OH point group given for the T2G irreducible representation, the character of C3 operation is going to be equal to 0 here, because the character is 0, while for character for EZ is going to be equal to -1, and for C2 operation here, the character for T2G representation is going to be equal to +1, and for character for EZ is going to be equal to 0. Similarly for S6, you will see the character of T2G irreducible representation is 0, and character for EZ is equal to -1. For sigma H, it is -1 and +2 for T2G and EZ, as well as for sigma D also is +1 for T2G and 0 for EZ irreducible representation. So that is how we can figure out, or we can find out how the d orbitals are going to transform as in a given point group. We have taken the octahedral point group here as the example to work this out, because octahedral point group, we have different types of symmetry operations, and one can easily, or one can, once we do for octahedral point group, I'm sure we can do it for any other point group for a given molecule. So this essentially brings us to the end of this lecture. During this lecture, what we have done is we have found out how we can use the d orbitals as the basis to write a reducible representation, and as well as we know how to block factorize this reducible representation or matrices of this reducible representation into uh, block factored matrices of which represent essentially irreducible representations of the point group. So let me conclude this lecture with this, and I thank you very much for being with me during this lecture.